So I'm going to use Mark's computer to show you motion and simulation. But before that, I want to take an audience poll. Pretty flexible. I've been with SolidWorks for like 14 years, working on all the simulation products. Um, so unless my memory fails me, I should know a lot of things in and out. Um, and I know all the history of why we did some of these changes. So I'll try to be a little flexible here. How many of you have used Motion? Okay, there's a few of them. And how many of you have used SolidWorks Simulation, the finite element? Okay, few people. So is there any specific preference? Like, do you want me to focus more on simulation? Raise your hands. All right, a few people. And if you want me to focus more on motion, raise your hands. And I have worked, I think one gentleman asked me about flow simulation. Anybody here interested in flow simulation? Or you've used it or interested? Interested in it? And anybody with plastic injection molding call was interested? Those two are not on this machine, but I'll try to log into my machine at work and see if I can show you those two as well. So I'll try to cover all the 4 products in a more broader scope. I know a few resellers are present here, so always contact the reseller for some in-depth information and demos and any questions you might have. All right, so it's a mix of everything. I guess there's no one single preference. So I'm going to start with motion. And bear with me, I'm using Mark's computer here. Because I've made these files available to Mark and Carl. It's on his computer, so you can grab these files. And whatever I'm going to show here are from those files, the steps. So you can always take it back and recreate those steps with these files. I've done it in 2015, knowing that a lot of people will not have migrated to 2016. So if there's anything new in 2016, I'll mention it as well if it's not here. So everybody's able to see the screens. In my PowerPoint, I had videos, but since I shared with Mark, it's stripped out this video of the motion. But at a high level, if you look at motion, it's an add-in inside SolidWorks, but now it's part of SolidWorks Office Premium. So SolidWorks has like every product line is divided into 3 products: the standard, professional, and premium. So you have SolidWorks Standard, Professional, Premium. Similarly, you have Simulation, Standard, Premium, and Simulation Premium and Professional, Professional, and Premium. So motion and statics from simulation is part of SolidWorks Office Premium. So if you have SolidWorks Office Premium, you should have those bundles. So the plastics is again has its own standard, professional, premium bundles, and Flow also has just one bundle, which is, we used to have a standard and professional. We got rid of it as just Flow simulation, and then there's some add-on models like electronics and HVAC. So for motion, it's part of SolidWorks Office Premium. It works on assemblies only. That's what I show here. It does not work on parts or drawings. So we need assemblies because it needs mates and it needs interaction between bodies. At a high level, every assembly can have multiple studies, or what you call as what-if scenarios. And that's what you're setting up. So you start with your assembly with all the mates, and then you decide you want to do a motion study. And you can do any number of motion studies within the assembly. And all the results are stored within the assembly as well, the study and the results. And behind the scenes, there's a solver running to compute all the results. So at a high level, motion and in SolidWorks, all the components are rigid. It's not flexing. So motion takes the same assumption. It's all rigid. So if you have something very highly elastic and it's all bending while it's moving, motion is not the right tool for you. You can use either some FEA tools. There are also some flex body motion tools out there. Our sister company Simulia has a package called SimPack which can do that. So if you want to do that level of high analysis, like you want to do tire on a car and how it's flexing, then you would probably use that. So because it's rigid, it's got 6 degrees of freedom, 3 translations, and then 3 rotations. Uh, and your mates try to take away these degrees of freedom so you get the right behaviors, and then you apply motors to take away more behaviors, or apply forces. We do have some springs which you can also apply to give that interaction inside motion. I'll show you that. So this is just a simple analysis of a shaft going inside a sleeve and how it's a concentric made on SolidWorks, so which allows the rotation and the translation because it's a mate. So you have 2 parts. Each part has 6 degrees of freedom, so you have totally 12. Because one is fixed, it takes away 6 degrees of freedom. Because the shaft has a concentric mate, it takes away 4, which means you're left with 2 degrees of freedom. So it can rotate and it can translate. So it's up to you what you want to do with those 2 degrees of freedom. You want to apply a motor or you want to apply an actuator to drive that motion, and that's what we'll do in motion. Now, let me start off with an example so you get a hang of what's going on with motion, and then we'll come back to this. So any questions so far while I show you? All right. So this is just a landing gear. So this is connected to the plane, and the landing gear comes out. And it's driven by this actuator here, which actually drives the landing gear to open and close. So in SolidWorks, you would just move this part and you'll see like an open and close position. Typically, people for showing open and close positions would use like configurations. They would put a distance made of the actuator, which is what I have here. So I've got all the parts. It could be sub-assemblies. Um, I have this distance made here, which actually constrains that. So I can change the distance so it goes, opens up and closes if I want to create 2 configurations of that. Now, I'm going to create a motion of this, trying to put a actuator function or actuator constraint on that part to actually open the landing gear. So in the assembly tab, there is a button called new motion study. That's how you start motion. But before that, you would go to tools, and I think it's very dark here. I'm guessing this is tools, okay. And in add-ons, we have SolidWorks Motion. And for simulation, we'll use that. We'll come to it in the end, later on. So I'm going to say motion, and it's loaded. There is no menu items on top. It is part of the study. So all the commands you want to use in motion as part of the study. So once I create a new motion study, it's going to create a tab in the bottom. And you can create any number of studies here for that assembly. And all your motion commands are here. That's it. There's no special menus. Everything you do here is here. Or there's some commands here as well, like checking interferences and things. Will come to it. And then there's the timeline here. So between these 3 items, you can set up all the functions for motion. So where will I use motion? So one of the things I like to do with motion is to find out if there's something flying away. So I would just drag this. This is the topmost node. This is what we call as key points. To anything, this is the time. I can drag it to 4 seconds, 5 seconds. And I'll just add gravity here, acting in the y direction. And I'm going to change it to motion analysis. So there's 3 solvers we'll come to in a minute. So I'll just do this. And before I start the simulation, I'm going to suppress this distance mate. And just run it. And that's it. That's all I would do. We'll come to these errors later, but that's all to see if anything is flying away. Now it's behaving as I expected. It has to go down and come back. But if something was not connected properly, it might fly away. Then you would go put a mate to constrain it. So that's the first way I would just start off with motion, if you want to. You don't have to put gravity all the time, but this is one of the ways I use it. So for any motion study, you would start a new motion study, and it'll use all your parts and mates, and then you try to set up your motion simulation. So this is the first thing people do. Now, how many of you here do animation? Any of you interested in animation? Okay, a few people. So there are 3 different ways you can present a motion analysis, or you can present your motion. One is animation, it's just for presentation only. So you want to show something quickly to your boss or manager or your client. You can just move things around and it just works. So as an example, let me show you here. I would say go to animation. Let me go ahead and suppress this. Actually, let me do this. So here it is at that. I'm going to go here and I'm going to edit this distance mate, and I'm going to make it maybe 5 and see what happens. And let's see if, yeah, that's it. So just animating it. You can move things on the screen. It's going to record it for you, and it just will animate. No physics. It's just going to do what you're trying to do. It's very useful for things like explode, collapse, views. You can get in those if you already have explodes and collapse set up here. You can bring it as an animation here. You can change colors of the parts. You can hide and show transparency so that you can see what's happening inside parts. So it's mainly for presentation, no physics. You're not going to get any engineering results like forces or accelerations or velocity. So you decide upfront what you want to do. And if you want to have some rendering on top of the animation, you can add rendering to this as well, or you can add it to motion as well. You can do it at both places. So if you already have a rendering scene set up with photo view, then you would add it in here as well. So when you save this as an animation, here you would set up that buffer. You would say PhotoWorks. If you have photo view rendering, you can say capture each frame with the actual rendered image. Now, so that's animation. So let's go back to the motion study. And motion analysis is the other extreme. So it is physics, actual physics is happening here, and we give you actual forces and velocities and acceleration. So animation is for presentation, motion analysis is for engineering results. Now, basic motion is something we tried as an intermediate step. We hooked up a gaming engine, which can do some physics like springs and contact, but it's still a little approximate, and it won't give you any results like forces or accelerations or velocity, but it can do contacts because animation cannot do contacts. Animation will just, if you want 2 parts to go through each other, will just go through each other. You can just set it up that way. So you decide. From my experience, I know Jason's one person who's got a lot of experience with motion. Not sure a lot of people use basic motion. Either they use animation or they use motion analysis. But you can try it out and see if in some cases it works for you. So I'm going to suppress this mate. The only reason I have the distance mate is I can always get a starting position always, because I might move things on the screen. I might go back to the model tab, change something, come back here. If I want my motion to always start with a starting position, I have these position mates, and I can always suppress it in motion, and it's not going to affect your SolidWorks model here, where it's still going to keep it suppressed. But at least in the motion, you can start off with some starting position always if you want it that way. That's the only reason I've set that up. I suppressed it there. Um, so then, we have gravity. I'm going to set up the actuator here between the two. So I would use the motor function here. I've got a rotary motor for rotation and a linear motor or actuator for translation. So in this case, it's translation. I can select any geometry, so it pulls up an arrow on how it's going to move. And it's with respect to this part, which is this cylinder. This is important to do. If you do not select this part here, it'll assume that that is attached to a fixed ground, which means the position will not change. So if it's fixed, uh, it'll only keep the arrow in this direction, it'll never change direction. But in this case, the actuator is actually rotating, the cylinder is rotating, and it's also pushing out. So the direction of the push is always changing as it's also rotating. So you want to make sure you set the base on a moving part, not on a fixed part. So this is a common mistake people do. Oh, I just got a motor, I got an arrow, I'm done. But there's a little more physics involved here. Um, we can make it a little more easier to do, but right now this is where we are at the user interface. So that's something I do. And then it's by default we use a constant speed motor. Um, I'll show you both ways of doing it. First, I'm just going to give a distance of, I think, 7 inches. It starts at 0 seconds and ends at 5 seconds. And you can get a graph here. If you double click on it, it'll tell you this is how it's going to create that function. And that's it. So I have the motor set up. One thing I do find useful when I'm doing only the setting up the motion part, I don't want to see the parts. I would just actually filter only driving. So I have a cleaner tree while I'm setting up the motion. And then when I'm doing the results, I might need some of the other things. And I solve it. And that's it. Now, what can you do with this? I can create a video out of it. I'll just create an AVI of this, which you can then open and or send it to anybody. Or I can say, okay, now how much force did it take to open, to do this motion? All your results are part of this results and plots. That's the only button where you get all your results. So I can click on it. It's selected the motor from the tree. I can say I want a force. I want the motor force. Give me the magnitude. And this is a force that's going to crank out um, for what you've asked. So that's how you get engineering results out. So any questions? So this is the general procedure I'm going to use to solve any motion. It's going to use your mates. It's going to use your part geometry. We only support solids, so no surfaces, because we need the mass and inertia. Yes, go ahead. So to get the results there, you could have all the material properties. Right. Yeah. So it grabs all that from the SolidWorks that we are talking. We already have that defined there, and for those mass properties, also you don't have any other questions?
this for? You're showing points like point 1, 2, they're just all over the place. Are you using those, or you just have them displayed?
Oh, those points. Okay. No, those are for, that's a good question. So these are all the points on the screen. Um, I use some of these points for removing a concept called redundancies. And we'll cover that a little later on. I just use, these are some for some advanced mating. And we'll cover some of that later. I'll come to you. For now, you can ignore them. You can assume that you just go to your assembly and you just did this motion and it ran. So I'm going to go back to my PDF. So once now you've seen the motion, so you have parts, which means that you're adding degrees of freedom to the system. So anything which is a moving part is going to have 6 degrees of freedom as far as motion is concerned. You're going to use mates and motors to take away some degrees of freedom. You can also add forces and springs because they're coming from the environment, or somebody is sitting on a scissor lift. You don't want to model the person. You can just put that equivalent force. You have springs. You don't have to model the spring. You can give a spring element. Actual geometry of the spring, you can say it's a compression spring or normal spring. And motors and mates take away degrees of freedom. And this is important because in real life, you might put a motor, and if it needs, say, 20 pound inch torque to actually rotate it, but you put only 10 pound inch, it's just going to get stuck. It cannot push it. But here, since it's a constraint, you're going to put it as a displacement. You'll say move 45 degrees. It doesn't matter how heavy that part is, it's going to move 45 degrees because it's a constraint. Which means when you look at the result, you're going to have like a huge force on it based on what the physics is. And I'll show you some mistakes as we, not mistakes, I'll show you some of the examples when I get a customer call. Hey, I gave a contact condition between these two parts and I also have a motor. Somehow the contact condition is not working. Why? Because you put a motor and that's given first preference, and it will solve for that because it's a constraint. And that's where the forces come in, where you can represent the same motor as a force function, which will actually behave more close to what you have in real life. So there are cases where you want the motor because it's easier to define, the cases where you want to use a force. You can use both ways. So that comes down to two different things, kinematic and dynamic analysis. If you take a simple, there's an animation here, a 4-bar mechanism. If I define a position of one link, everything else, every other link is fully defined. But if it's a dynamic analysis, that might not be true because some external forces will decide actually how it actually moves. So the way you can check this is we have a degree of freedom calculator in our software, where you can say, okay, how many degrees of freedom does this mechanism have? And if it's greater than 1, which means there's more than one solution for your problem. And if it is 0 or negative, if it's 0, you're great, but if it's negative, you have redundancy problems, and I'll come to that as well. So this is where in motion study you would go to mates and say degrees of freedom, and it's going to give you like how many moving parts you have, how many mates you have, how many motors you have, what degrees of freedom it's taking away, and it's telling you that, hey, you have only one actual degree of freedom. So which means there's only one, when I look at this problem mathematically, there's only one degree of freedom in which is free, and you can put a motor. So this, if you put a motor to that, then it becomes a pure kinematic analysis. But if you leave it this way, it's a dynamic analysis and it's waiting for some forces to actually dictate how it goes. Maybe gravity or a force to decide how it goes. So that's how I would look at um, kinematic and dynamic. And this is number of redundant constraints. Because this is rigid body motion, the best example is your door hinge. The whole door itself is one rigid body. It's only got 6 degrees of freedom. So mathematically, I need 6 equations to solve this door. But each hinge removes 5 degrees of freedom because it can only allow one rotation. So mathematically, you're giving me 15. If I have 3 hinges, you're giving me 15 degrees of freedom because I've got 3 hinges. My door has only 6. Now, which 5 or which 6 can I use for this door? Or 5 I can use because hinge is only 5. So which means the remaining 11 or 10 I'm going to throw away. And that's what it's doing here. Because if I cannot throw it away, then there's 2-3 degrees of freedom fighting for the same equation. It will not solve. So it has to throw it away. Now, because this happens, when you look at the results, you'll see all the load going to one hinge. And the other 2 hinges are going to get no load. And I know Jason's worked with a few things with scissor lifts, where it's a symmetric model. It's on both sides you have the similar mates. You just need one side mates. And then they're like, or I'm using 2 actuators to drive one motion. Only one actuator will get all the load. So that's where you would use the force-based function for a motor. So it will compute the forces on both sides. We won't go through that. It's more advanced here. Might be critical. I have some examples I will share. I've not shared it here, but I'll send it a call and see if we can post it, how we would tackle that. So I think this is a little important. I know it is going into the trenches here. It makes it a little thinking more complex, but this is engineering. It's not as easy as what you see is what you get from SolidWorks. You need if you're doing just velocities and accelerations, you don't need to worry about redundancies. Should be okay. But if you're trying to look at joint forces, this is going to play a big impact, because if it removes redundant degrees of freedom, you're not going to get any force there, and that's not right. So there's ways you can get around that. So I won't cover that here because there's more of a 101 type of thing. These are more advanced techniques. Call has my contact, or you can take my card. If you have any issues like that, send me an email. Talk to a reseller. They have some experience with this. They can help you out as well. So any questions? So I'll skip all this because we got to cover a lot of things. So from what you're doing from your application, is there anything specific you want me to focus on in motion? I'm going to show you some other things in motion as well, some debugging tips. Is there anything specific you want to focus on, because it's mechanisms you're going to be working on? Any questions so far? Well, okay. So this is what we covered right now. I know you're going to be creating a lot of assemblies with if you want to do motion analysis, here's some tips. You might feel very comfortable saying, okay, I'm going to fix this part to this part using a fixed mate, or having 3 mates, which will actually fix this part to this part. It'll work. It just makes it a little more not burdensome, but I'll say it has to now solve a little more. So it means it might take a little longer to solve. Motion analysis takes if there are no contacts, it should be fairly quick. But then it's going to do that extra step. So if you think it's not going to move, just fix it. Don't worry about putting mates between these fixed parts to fix it. So it just makes it a little more efficient. And try to create mates as close to lifelike as possible. And I'll tell you an example. Now, if you have like a, say a shaft going into a sleeve, so try to put all the mates between the shaft and sleeve together for all, like for the coincident, for the concentric. Don't do coincident with the shaft, but concentric with some other part which is connected on the other side of the shaft. It just now has to solve through A, B, C rather than just solving A and B, which is the shaft and the sleeve. So it just makes it a little more harder for the, not harder, I would say it just takes more equations for it to solve properly. So if you can efficiently just make it like how it is in real life between these two, just do those mates with these two. I know you use a lot of reference planes in the main assembly. You might have use axes from different parts because it's just convenient and right there. You might have washers. You might use the washer face for one, and you might use the nut face for the other. Um, and so try to keep it as real life as possible. And use rigid groups. I'll come to this as well. So basically, you're trying to create less equations, faster solve, and also it helps you with, and also make it less redundant. And here are just few examples. I'm just going to look at a very simple example and a very complicated example. This is you're not going to see this inside the software. This is something one of our developers created inside MATLAB. He took the Sardox tree structure and tried to interpret how the solver is going to take it. And if you look at this diagram here, like how I mentioned, a lot of interconnection parts when this is connected to this and this and this. While here it's just connected, the same green part is connected to only these two. Just by cleaning up how it's all mated. And it becomes more efficient for the solver for the simple problem. And this is for a very complex problem where he's able to clean it up to make it a little more efficient, remove redundancies, remove the number of constraints, because Sardox, we let you mate it any way we want. We don't put a lot of restrictions on how you mate things. Yeah. Go. Right. It will solve it. It just takes longer to solve. It's not going to complain. It's just efficiency. It's going to honor whatever you left the model with. If it's got all these three rotations, it's going to take the three rotations and it'll just solve it. It just makes it slower. That's all. So it's going to solve, instead of solve here in the original model, instead of solving 733 constraints, it's going to solve 179 in the optimize, but it's going to still solve it. So we'll just see an example of that. So for the fasteners, there is one limitation I'll mention up front. SolidWorks does have an option to lock rotation. So if you now click on the mates, I think it might be a 2015 feature or might be a 2016. I saw it allowed to check. But you can just select the mates in the SolidWorks tree and say lock rotations. And it'll just lock it for all the concentric mates. It's very useful for the fasteners. Motion does not use it yet. But that's something you can do at the SolidWorks level to make it a little more efficient for solving. And the other trick you can do is we do support flexible sub-assemblies, and within this flexible sub-assemblies we have all moving parts, but you know this main assembly is fixed. Then just fix all these parts. It just makes it more efficient. So in this example, I'm just worried about this part here. So if I go to the motion study and solve it, you'll see that it takes a longer time to solve. And I'll open the pre-optimized version, and I'll show you what is fixed there. So if I know, say for example, this whole group is going to move together, I can just go ahead and select all these components. And inside motion, I have an option to make it, where's that? Where is make virtual? Ah, come on. Yeah, I can make it into an add new rigid group. So basically, you're not disturbing the SolidWorks model, but for motion, you're saying all this move together. So fasteners is one example. If you know, like the tire has 6 fasteners, and it's all bolted to the main shaft, they all move together. Instead of having these concentric coincident and for all the washers, for everything, you can just select the whole bunch and say this moves as one rigid group. As far as motion is concerned, it's one part. It's going to ignore all the mates between the nut and bolt and everything. Just makes it more efficient for the solver. So that's something you can do at the motion level, where it creates this rigid group here and does not disturb anything at the SolidWorks level, but it makes it more efficient for motion. So that's one of the tricks you can do inside motion. So now it's going a little faster compared to what we had just shown. So that's what I'm trying to show in this example. And the final part before I move to simulation, and a lot of people are interested in simulation, is to look at when you use motors was when do you use force. Again, I told you it takes away degrees of freedom. So in this example, if you put a motor here and it's going through this plate, the motor will always win. If you have a contact between this part and this, the motor is still going to win. So if when you're doing a problem, you think it's not working the way you intended, it's because of the motor. So instead of a motor, you can turn it into a torque as a force-based element, then it should work. At least more closer to what is happening in real life. So you have to decide what you want to do, because it's harder when you're using forces. Why would we always keep using force or torque and not have motors? Is now you have to create a special function if you want the motor to go at 10 millimeters per second, but still give enough torque. It has to be a variable torque to keep that 10 meters per second. It's harder. So we already have these. With a motor, you can just say go 10 meters per second. Depending on whatever physics is happening, it'll take all that into account and still keep it at 10 meters per second. So it's just easier to do it, and most of them use that. But in special cases, like if you have two actuators driving the same motion, you might want to use the forces. So again, if things are not working, try to turn off everything and turn it on in this order. Like turn off all contacts, check the drag behavior, turn on gravity, turn on contact, turn on forces, turn on motors in this order, so that you can start debugging where the problem is. All right, and these are just parameters, advanced parameters. I won't go through it because I want to switch to simulation. I know Carl is giving me a lot of time, but I want to. And so I've put on a lot of information here. It's I've given it to Mark and Carl. So why some of these solver parameters are important, why where we use it for different types of analysis, what you can try if you have failures. I've given all these notes here. Again, 99% of the time I've seen people position the assembly for position, not for function. So a lot of cleanup is required, because they might just say two planes and it's coincident. For motion, it might not be how it's in real life. Or they might just fix a lot of things because they just wanted to look right in the right positions, but that's not what is happening in real life. Um, um, And then you don't have to think of what you're trying to solve. You don't have to include every hardware, every piece based on what you're trying to do. Maybe it's just a subset of things you want to try. And one example, like scissor lift case, you don't need the 1,000 washers and the small pins and everything. You can just take the equivalent mass and put it at those locations. Um, it depends on what you're trying. If you just need the pin loads, you don't need the washers and everything. You just need those two, based on the weight of the whole boom, it was already small washers. You don't need that level of detail when you're doing a motion simulation. So you have to decide what is enough. Um, and you can always make changes at the motion study level for the mates or for the positions and not affect the SolidWorks motion. And you can have multiple motion studies within the assembly. So this is a sort of a quick introduction to motion. I've given all the files. Play with it, send me an email, talk to a reseller if you have any issues. So any questions before we move to simulation? I think a lot of people are interested in that. Yes, sir.
On the way that you make go down, how hard would it be to go ahead and make it go back up?
Oh, it'll be very easy. Oh, the landing gear problem, right? Yeah. Oh, it should be very easy. So one of the things in 2016 which you might find useful even before you do motion is something called as a mate controller in 2016. It's inside SolidWorks where you just select the distance mate and say position A, this is at this distance, position B, this is at this distance. A very simplified UI, and then you just say animate, it's going to animate through the positions. You don't even have to use motion, but you can take that information to motion. Something there. But coming back to what he was asking, so I'm going to say new motion study, motion analysis. I'm going to suppress it. I'm not going to use gravity right now. I can use gravity, doesn't matter. Linear motor. And I'm going to use this, and then I'm going to use something called as segments. I use distance, which just goes one way. Now I have to go this and come back. Inside segments, this is a more powerful tool where you can set up your own profile, a lot of different options. So for what Jason's asking, say I'm for 5 seconds, I'm going 7 inches. For 5 to 6, I'm leaving it at 7. I'm just leaving it there. And from 6 to 11, I'm going back to 0. This is a function it's going to take. So it's going to go up, stay there, come back down. This is the displacement profile of that what you've entered. This is the velocity, acceleration, and jerk of your profile. And you've got a lot of things like, okay, do you want a cubic interpolation, linear interpolation, polynomial? So you can control all these features here. You can save it, so you can use it in other functions. You can import a file. You can write your own custom function as well with this UI. So I'm not going to go all the details. And I'm just going to run this for 11 seconds, or I can just right click. I should close it. And I have to go back. I can say edit the point, 11 seconds. You can go up to like few days or 1/1000th of a second. So both extremes you can do with this. And that's it. It's staying there. It's coming back. So you should be able to get full control. Yes. Huh? Okay, points are, so if you look at, initially I've done it, if you look at my mates, I've used hinge mates. If I use a concentric and coincident, it is 7 degrees of freedom because concentric is 4 and coincident I think is 3. But there's some common degrees of freedom for both, which means they're redundant. One of it is redundant. So with hinges, I needed a point on a plane for coincident and on two axes or two concentric faces to keep it at 5. So that's why I created those points. It's just my way of mating. It also helps me organize my things. So that's why all these points are used for those hinge mates. And I also use points for something else. If I'm interested in the forces, thanks Jason, now I can actually set the mate location because that's where the forces and the moments get applied or get calculated. So if you know physically, if I just take two cylindrical faces, we have some math to figure out the center point where the mate location is, where all the forces will happen. But if you have two planes, the point could be arbitrary. Or if you have two axes, it could be anywhere along the axes, which means it's moving here and that point is there. You've created a big moment between what's moving here and the actual mate point. So you sort of use points to dictate where motion has to calculate the forces. So that's where also I use it. Because one of the things you can do, I don't have time to do it, is I can actually do a stress analysis by transferring the forces from those parts to that actual part and do a simulation right here in motion. So it'll freeze it at that step, get the forces, transfer it, do a FE analysis and give you the results. It's not flexible body where actually the part is actually deflecting as it's moving, but it can just freeze it at that frame and say this is the stresses at that part. So the points also help me make sure for simulation it's at the right place. So yeah, I can spend like 2 days going through every functionality. I know we're short on time, but I'd love to come back in the future if you want more in-depth analysis. All right, so let's go to simulation. So I'm going to just take a time check with Carl. So Carl, how much time do I have to go over simulation? I might need 15-20 minutes. Do I have that? Okay, all right, great. And so this is more from why you have to do simulation, but it's basically you want to get the best design for your stiffness or strength, right? You don't want it to break in the field, so you want to optimize it so that it'll work. Now there's various things when you start simulation. It might like, oh, it's for analysts, it's finite element, it's all complicated math. We are trying to make it easy, but we also face this problem. If we make it too easy, people make mistakes. So at a high level, there's a lot of things which could actually affect your results. You have the geometry itself. You have and the amount of detail you put in the geometry. Not everything is very simulation friendly. You might put very tiny fillets because for aesthetic reasons, but for simulation, it's going to increase either efficiency or it's going to take a long time to solve, or it might just be too much detail for simulation for what you're trying to do. So that affects your results. The material you're using affects the results. Element type will come to it while I do the demo. It's almost like sometimes garbage in, garbage out. So the more you make it, you represent the interactions, the boundary conditions to what is happening in real life, the better results you're going to get. We can make some assumptions at the virtual level of setting up. This is what I think it is, but that affects your results. So that plays a role. The mesh plays a role. And then you have to decide what type of study are you trying to do here. Is it thermal effects? Is it static? Or maybe it's dynamic, it's vibration. Everything has a different physics, so you have to decide that as well. So I'm not going to scare you with, hey, that's just too difficult. I'm just telling you up front, these are things which could affect your simulation. We have made it easy, and I'll show you in a minute how easy it is. But at the end of the day, you have to decide, because all this affect accuracy is what you're trying to get. You're just trying to get trends or insights, or you're going to get exact result at that location so you can match it up with your strain gauge results. So it depends on what you're trying to do. And that's how you would approach the problem and what you're trying to do. So I'm going to take a simple bracket. It could be, I'm going to start with a part analysis, then we'll do assembly, same steps of assemblies as well. But I'm going to start with a part just to show everyone how it is done. For some people, it might be boring because you've already done it. Apologize, but so assume a bracket during its lifetime. This is a bracket on an aircraft which is connecting the wing on one side, on the main frame on the other side. And during its operation, it could go through many loads. One is it's a vertical load, or it's a horizontal load, or a torque load. So what we call is different load cases. So I'm going to set up this in simulation and see if our parts will pass or fail. Is it going to break for these setups? So I'm just going to do what we call as a mechanical simulation here right now, or a structural simulation in SolidWorks. So is there anything specific people want to look at from a mechanical structural simulation? Any specific requests? Or is this okay? All right. So I have the part in SolidWorks. It could be a part assembly, multi-bodies, weldments. It's okay. For us, as far as simulation is concerned, a single body part is a part. Multi-bodies or assemblies are assemblies. Again, it's the add-in. You have the simulation menu here. But I always use two things. Start off with the command manager, but once you have the study, so that's the first thing you decide is the physics, is I'm going to go with static. There are all the other types of physics. I think this is a SolidWorks Office Premium license, so it only has static, but you have the other things at professional and premium level as well. It did pick up the material from SolidWorks, what you have defined, but you can always change it here without affecting the SolidWorks material. Again, these are studies in the bottom, similar to motion. I create studies, and I'm going to create a fixture or a restraint or a boundary condition to fix it. Maybe in real life these are bolted, but since I don't have the assembly parts, I'm just going to give the equivalent of the bolted connection here. First preference would be to just fix it, but you're going to over constrain it because with the bolted connection it can move a little up and down or it can rotate. So you have to decide what is actually happening in real life because if you over constrain it, it's going to create high stresses. Maybe that's not what's happening in real life. So I'm going to create a fixed hinge on all these locations, which means it can rotate, but it cannot translate or it cannot expand. And there are other types of restraints as well. You can specifically put in any direction you want something. So there's a lot of flexibility. You can use symmetry, you can use cylindrical coordinate systems. So a lot of flexibility in what you want to do. But now I'm just going to take fixed hinge and say, okay, so it's constrained. And I think view hide all types. No, view. I'm going to do simulation cells. Okay. And I'll come to you why I've created all this reference geometry for my load cases. And I'm just going to create a force on this. I'm going to create a vertical force. That's my first load case. So I'm going to say selected direction. I can just use this face or I can use the plane. It doesn't matter. Some reference geometry. And I'm going to say it's in pounds. I think it is 4,000. And it's going up. Yeah, it's going up. So that's good. But this is something you have to be critical. Is it on each phase is it 4,000, so total is 8,000, or the total is 4,000? In our case, its total is 4,000. So that will affect your factor of safety and your stresses. So be careful. That's why we have this. It's total 4,000. And that's it. I have to run it. This is as simple as it gets. Now, so let me close this. Oops. Okay. And these are your simulation results. The first thing I would do is look at the displacement and animate it. Okay, is this behaving the way it's supposed to behave? That's the first check I'll do. Does this look like it's behaving the way I want it? Yes. Okay, so now I can look at the displacement results, or I can right click on results folder and select displacement. You got stresses, factor of safety. I can say displacement. I'm going to do the resultant displacement, and I'm going to say okay. And this is a plot I get for that displacement. And if you want to actually probe the values, you can probe the values here. So it's going to give you those values here. You can change the units. So you can double click on the legend. You can go to definition, change the units to inches. I can come here, change it to floating, so I have a little more granularity on the results. So there are a lot of things you can do. You can do section clipping, look at the stresses inside. So you can look at the stresses inside. So there's a lot of these post-processing functions you can do, and also you can look at the stresses. Again, same thing. I can change it to PSI. I can right click, change the component here at the legend level. Maybe I want a different stress. Sometimes people seem to like the discrete plot instead of continuous. Looks better, so it's the stress value is a little more separated out rather than a continuous flow. And you can animate it. You can save it as an animation, right? So this is how easy it is. But there's a lot of things behind the scenes which happens, which I'll go through in a minute. Any questions so far before I go through all the more advanced stuff? So this is the same workflow I'm going to follow for assemblies. Same thing, create a study, create my boundary conditions, create my loads. The additional thing you have to do is connection between the parts. How do I treat all the parts? How do I connect them? We can do some connectors. I can do bonded. We'll go over one assembly as example. But this is the most basic workflow for any problem. Any questions? All right. Now, I've run, I've got these 4 studies set up here already for each load case, which is what you would do in 2014. Every load case that's acting independently, so you would set up these studies for that load case. In 2015, we added something called this load case. So for example, I'll take this horizontal load, put it here. I'll take the vertical load, put it, already have the vertical load, that's fine. The 42-degree angle load, which is why this plane is there. And finally, the torque load. And that's why you have that axis. And what happened here? To have the 4, let me delete this one. For some reason it did not copy. So let me try again. Horizontal. So let me try a different way. Okay, it worked. Right, so I've got these, but I can create these 4 load cases by something called as load case manager. And wait a minute. Is that 2016? That's 2016. So we have a special load case manager. No, wait a minute. I thought it was 2015. Okay. Load case manager is for a simulation professional. They have SolidWorks Premium, where it has a nice UI setting up all the load cases. It'll run each load case. But also the benefit of using load cases is you can do something called a secondary load cases or secondary combinations, where you can say this load and this load acts together, what happens? If this load and this load act together, what happens? So you can do all these combinations from just the primary load cases. So when running it, it's going to do the primary load cases and just add up for all your secondary load cases so it's faster. And then it's got some nice post-processing to track the factor of safety for each load case. It's got a nice table so you can compare all that in one place. So you don't have to go switch between studies. Now, one thing I'll do is I'll run all studies right now. So this I think is new in 2015, where it gives a nice preview of what studies are running. In 2016, I think we have also made sure you can now select which study you want to run instead of running all studies. So those are small improvements we've done. Right. Now it's done all this. I can use compare results. And I can say all the studies in this configuration. I can compare the factor of safety. Of all these. So it's about 2.3, 1.8, 1.8, 4.7. So we're okay for all the 4 load cases for this part. Then you can create a report out of it, and it'll capture everything for you in the report. What your inputs are, what your outputs are, what your reaction forces are, to give you a nice Word document. All right, so I'm going to spend 5 more minutes. I don't have it as part of this script, but I'm going to open another as an example model from here to just show you the assembly workflow, which is very similar to what I just showed you with parts. And I apologize, I'm going a little fast. I hope everybody understood what I was trying to do here. I'll have to exit compare. And one of the things from 2016, which I cannot show here, is for results. We do have something called as result equations. So with your results, you can now create equations. Sometimes people say my dynamic load, so I got a result for my 1 meso stress for 10 pounds. Now what would be the result for 30 pounds? So I'm just, instead of running the analysis again for 30 pounds, because it's a linear problem, you would just multiply the results by 3 times. You can do that as part of the result equations. And so you can create your own customized plots. One other use case is you can say divide the stress divided by the strain, which would actually give you the stiffness plot of the model. So it'll tell you where it's stronger and where it's a little weaker. So things like that. So, and then for stress intensity, we already now gave that plot as an item. You can do all the principal stresses added up to give the stress intensity. So things like that you can do in 2016. So I'm gonna need Mark's help here. Mark, I need to go to the examples folder. So can I go to the program files here?
Yeah.
2015. All right, so I'm just going to use this button here for assemblies. I'm just going to use a basketball hoop for showing a few things. All these are tutorial models, so you should come install with the software if you go to help and tutorials. And this is an example that will help you run the problem, set it up. And if I have 5 minutes, I'm going to also try to do flow simulation. One gentleman was interested, and also plastics Carl was interested. So I'll try to cover that in the next 7 minutes after I show this. Hopefully, Carl, it's okay? Okay. So again, you have to study. Very similar. Instead of just having one part, you have all the parts, multiple parts. Same again, each part is a part in your assembly, and it's getting the material or a multi-body. And this is something you already did. It's fixed in the bottom. You created a force here for the hoop. Somebody put a hand and tried to pull it down, a basketball hoop. So that's the force you're putting. The only additional thing you do here are the bolt connectors. So you say these are bolted. Again, these are connectors. So these are like idealized connectors. They are in between solving the real bolt and fixing it. So this gives you a little more realistic simulation of that of a bolt, and the load path will go through this bolt. But if you want to get results at the bolt itself, don't use that. Actually model the actual geometry. So you have to decide what your assumptions are. If you're getting results away from the bolt connectors are great. But if you want results at the bolt itself, create solid geometry. And then I have contacts. By default, everything is bonded together. So if you have a huge assembly, everything touching, it makes it as one big piece. But then you can supersede that with a contact, which is like the sliding. So it's more realistic. Takes longer to solve, but gives more accurate results. With bonded, you might think, oh, the stresses are not too much because internally it's all made it into one big giant body, which is not what it's in real life. Once you put contact, the stresses might go up because that's what's happening in real life. So decide, so here for creating the contacts, you would say, I'm creating a sliding contact between these two faces here, where the bolts, the two parts come in touch where the bolt connector is. So when you run the analysis, and then I'll just talk about the mesh. I didn't talk about that. And our tip for that. So this is where it's going to take a little longer time. If it was bonded, you wouldn't go through the step. The analysis would be done. But we have contact, that's going to take a little longer. So any questions while it's solving? We do support we support multiple processes. The solver does support it, so it's trying to use all the solvers, all the processes. We do not support GPU at this time. If you think you need that, file the enhancement from the customer portal. We're tracking the number of hits for that. What else have some people asked? And sometimes it'll tell you there's some large displacement if something is not fixed properly or you put too much load. Because this is a linear static analysis, displacements are small. That's what we assume. And then you get the stresses, displacements, you can animate it. Everything very similar to what you did with part analysis. So any questions?
Yeah.
Yeah.
So you did.
Oh. Sorry.
I was going to ask about the bolt connection. I think you can look at the stresses in the bolt itself.
Right. You can look at the forces. I don't know if I have to rerun it again because it's read only. Yes, you have the bolt check plot, which can give you the forces on the bolt. It comes in the report, what the shear forces are, what the axial forces on the bolt are. I don't think we can look at the stresses, but you can look at all the forces going through the bolt. Does that answer your question? Yeah. Anything else? All right. So this ends our simulation. This is where you compare results. Again, at the beginning, before you start a simulation project, decide what you want to get out of it. What are your critical components? There's a lot of things you can play with, and you can really get lost. So try to upfront decide what you want to get out of simulation, and then tackle it that way. So now I'm going to try something here. See if I can access my work computer. So Mark, I'm just going to use the internet. I'm not stopped anything here. I just needed to use this. And I'm going to see how well technology works. So far, so good. So far, so good. Excellent. Excellent. All right. So again, flow simulation is an add-in, similar to the other simulation tools. Plastics is an add-in as well, right? So again, like motion or simulation, it's an add-in, and so that's how it works. So I'm going to start with, let's just start with a simple plate or a box for plastics. Actually, maybe let me do something a little more complicated. Plastics. Or this is just too complicated. Okay, let me try something else. Okay. Actually, maybe this is good. So I'm just going to give you some basic information of plastic injection molding and then show you what plastics can do. So if you look at a typical injection machine, this is where the plastic pellets, it's just plastic material which comes in. It's like spherical balls or in some shape which comes in. It gets melted here. So if I look here, and this is where I'm just showing you the animation of how it actually works. This is a whole machine. The screw is running, so the plastic material is getting melted, and the shear itself from the screw will melt the plastic even more. And then it gets injected through the mold. It's almost like a cake. What do you call it? A cake. To make cake, you have the actual cup or the cavity where you put the batter and bake it, and you get the cake for that shape. Very similar. This mold has the cavity, so plastic gets injected here, and then there's cooling liquid going around it, and then once all the plastic is injected, it's being also cooled, And then when it's not fully cooled yet, it comes out. It's still a little hard, so it doesn't deform. And then it ejects it out, and it just cools outside. So this is a typical injection molding process. So where plastic comes in is it can take this part and actually inject that material. So it's in a sense, it's like a flow simulation, but specific for plastics. So you can actually simulate that